project. These have been delivered actually as part of the Pacific Next Gen project, and they are still CMIP 5 based, but our CSIRO project team have really combed over the CMIP 5 data and improved the sea level rise projections from these. These will be delivered to Vanuatu in a report, but they're also a component of what we're delivering in this KIRAP project. So there's just a table of, I guess, the most salient findings of that, which is the sea level rise projections under 3 different scenarios out to 2100 in the bottom. Please let me know later during our discussion period if you have any more questions about this or would like the data in a different form or anything like that. So, of course, sea level rise is only one of the things that we need to think about in terms of coastal risk and climate change. You know, sea level rise generally refers to the climate timescale movement of the sea level or mean sea level in this diagram. But of course, if you're actually on the coast, there's a host of other processes that change the water levels at much shorter timescales, like tides, storm surge, storm waves, and of course, your exposure to those kind of processes really depends on, you know, what island you're on, whether you're in a bay, whether you're behind a reef, and all of that. And we refer to that sort of short-term water level at any given location as total water level. It's just sort of a shorthand for when all of these processes come together in any location. So to estimate that throughout Vanuatu, we combine a number of different climatological products that are available out there. We have a historical sea level from a European reanalysis. We have a global tidal model that we use. We calculate the inverse barometer effect, which in Pacific Islands anyway, estimates storm surge to some degree. And we get wave information from our own, in collaboration with the Bureau of Meteorology, wave hindcast. And on the back of that, we can calculate some empirical wave setup and run up calculations. And so what that gives us then, when we combine those together and do some empirical modeling, basically it gives us hourly water levels for the last 40 years from about 1980 to 2020 in a gridded level across Vanuatu. And then we can consider how the statistics of these things might change through the Coordinated Ocean Wave Climate Project. One of the main directors of that is also actually in our team, Mark Emer. And then also, of course, those sea level rise projections that I just presented earlier become a component of that. And then the tropical cyclone information from KIRAP activity 1.2. Sorry, it's supposed to say 1.2.3, but again, we'll talk about that in a later project, later talk. But so just to kind of help visualize this, if you like, a little bit, here's just a plot of historical sea level. Again, that's that slowly varying sea level on a climate time scale. And then one of the median projected sea level rise scenarios. This one's for RCP 8.5. And so you can see, especially in the future, it varies slowly. But then if we consider our hourly total water level, so that's including the tides and the waves and the storm surge estimate, we can see that there's a lot more variation on short time scales, and it's actually quite peaky. And so to sort of get a better understanding of what that might mean for us, engineers and scientists often establish some kind of threshold based on an extreme value analysis of the data. And one that's very often used is an annual exceedance probability, or probably better called an average recurrence interval, or an ARI level, which this is, you've probably heard about, like a 10-year storm or a 50-year storm. What that really means is that's the 1 in 10-year probability that particular level will be exceeded. So you see in this case, we've got our daily maximum water levels for 40 years, and the storm surges that you can see in the peaks there cross that line 4 times. So on average, once every 10 years. Of course, that doesn't mean it's going to happen every single 10 years. You might get 2 in a 10-year period, and then none for the next. Of course, in the future, with sea level rise, if we assume that same threshold, you can see that it's crossed many more times. So that 10-year storm level actually has gone up. And so we need to calculate with climate change a new ARI, or a new 10-year storm level. And interestingly, the way the statistics work out, even if we project the old total water level variability into the future, it's not linearly the same as the sea level rise. This is known as an allowance. So what that means is that even with the same sea level rise scenario, 2 different locations might have a different average return interval, and then a different increase of an average return interval into the future. So it's really these kind of statistics that we're modeling. So again, what we've done using this regional climate information is we've modeled these changes in ARIs. Here you can see them for the 10-year and the 50-year storm tide or total water level out into the future. But whereas for the sea level rise projection scenarios, we only have one, there's only one projection that covers all of Vanuatu. Here we've calculated them for points, multiple points, actually over 2,000 points at regular intervals around the coastline of Vanuatu. And again, the idea is that this information can be used to understand when areas of land or go into inundation models, coastal inundation models, or help understand when a particular seawall or coastal defense might be overtopped or something like that. So, I guess in a quick nutshell, that's the way we are planning on delivering the information for this sub-activity 1.2.4.1, which is really the sort of the national scale preliminary data for this activity. But what I'd really like for us to consider in the discussion period of this workshop is, do these average occurrence intervals, does that make sense to the sectors and to the other KIRAP stakeholders? And if so, what levels should we consider delivering? We've just preliminarily calculated the 10-year and the 50-year, but we could easily do the 20-year or the 100-year or something like that. Again, I've presented in that last slide those coastal points, the regular points around all islands in Vanuatu. But we could consider some other format, such as gridded. To me, the coastal points make the most sense because we're again doing a empirical wave setup and run up calculation. And as you get away from the coastline, obviously that makes less sense. But also we could consider delivering other climatology products because I guess under the bonnet, we've got this hourly total water level, including information on tides and waves and other information. So if there are other climatological products that KIRAP stakeholders would like to see, then please let us know, and let's maybe discuss during the discussion period that comes after these series of talks. And really quickly, before I hand over to Vanessa, I would like to discuss some shortcomings and some caveats with this data. So this data is created from extant regional climate information that I showed in an earlier slide. That is a global tidal model, a global atmospheric reanalysis, a regional wave model analysis, and other information. But even that regional wave model, the Cocker Wave Hindcast, its highest resolution in Vanuatu is about 7 kilometer spatial resolution, which isn't really that great for resolving, small bays and individual reefs and things like that. So that's an important consideration here. We are trying to address that with the dynamical downscaling that Vanessa will discuss in her next talk. Also, I know this probably sounds incredulous to some of you in Vanuatu, but for any given location in Vanuatu, you don't actually experience enough tropical cyclones within this 40-year period. I mean, any given location may only experience 3, 4, 5 severe tropical cyclones over a 40-year period. So that leads to high statistical uncertainty in these ARIs for certain things like storm surge and storm waves. So we've got some ways to address that, and that will also be in the talk following Vanessa's talk that I'll give. So I guess that's it for me for now. But again, I hope we can circle back on both these questions for discussion and these considerations, shortcomings, and how we're planning on addressing them later on in this workshop today. And that's just kicking back to the agenda to remind myself where we're at. So please, Beth or Vanessa, take it from here.
All right, thank you. Are you going to stop sharing?
I'll stop sharing, yep.
Yeah, great. Well, I'm just going to share my screen. Let's get the right one here. Okay. So, oops, what's happened? Where have you gone? There we go. So you're seeing center mode? Yep. Oh, sorry, it keeps on disappearing from my screen. Is it disappearing from yours as well? Okay, it's back. Okay, so sorry about that. Oh dear, what's going on? Every time I move my cursor, my presentation disappears. Okay, so yeah, I'm just going to give a brief overview of the, oh, sorry, I'm not sure, are you getting this? My presentation keeps disappearing from my screen.
Yeah, a bit.
Has it gone again?
Yep.
What is going on? So I'm just going to stop sharing and try again, and hopefully it behaves. Sorry about this. Okay, is it going to stay? Right. Hopefully it does. So yeah, I'm just going to give a very brief overview of the dynamical downscaling approach that we're using, and just sort of give a bit of a better explanation as to what that really means. So as Ron mentioned, we're adopting a national scale approach of dynamical downscaling using a high resolution numerical model. And that allows for full consideration of the dynamics of extreme sea levels, waves, and additional processes such as currents. And it's called dynamical downscaling. Downscaling because it produces very high resolution information, both in terms of scales of space and time, from relatively coarse resolution input data that's provided on the model boundary, such as quite coarse resolution waves or elevations and velocities. And it's called dynamical because it does this by solving and simulating many complex non-linear interacting processes. So as we mentioned, the dynamical downscaling is using this national high resolution model, and it will be run over a 40-year period, 1980 to 2020, which we term a hindpass, producing hourly outputs of water levels at very high spatial resolution. And these outputs will be analysed and used to refine the coastal total water values that Ron spoke about, and also to refine extreme value analysis and recurrence exceedance probabilities. The model itself will also be used separately to simulate extreme event scenarios such as synthetic tropical cyclones, and Ron will talk about that in the next talk as well. Okay, now you don't want to move presentation. Okay, let's try this. Dear. Oh, there we go. Okay, so the model that we're using is called SCISM, and it's got a very long, that's an acronym for a very long name. which is a semi-implicit cross-scale hydroscience integrated system model. And I guess within that name, the cross-scale is important because it's designed for this sort of seamless simulation across these spatial scales from coast to the open ocean. It's widely used by the international scientific community for lots of coastal scale applications, including storm surge and coastal inundation. Just an aside, really, it's a model of choice for operational forecast systems in several countries, including Taiwan and Portugal, and also in California. So it's a state-of-the-art model that uses unstructured mesh and two-way coupling of waves and hydrodynamics. And I just wanted to just spend a couple of minutes sort of explaining why that's important. So in the top image here, you can see this is supposed to be, like I say, an island. And you can see these sort of structured grids that are made up of rectangles and squares. And it can be quite challenging for these sorts of models to produce a good grid where there's complex coastlines and bathymetries, and also across multiple scales. Whereas we adopt this model SCISM, which is an unstructured mesh. And because it uses triangles, and it's much able to prescribe complex coastlines and be able to define very well, for example, through channels, and pick up very fine resolution over specific features such as reefs, for example. So it also allows a change in resolution quite easily within the same domain. And I'll show that in the next slide. So this actually shows the model domain using our unstructured model for the national scale for Vanuatu. And as you can see, it's made up of triangles, in fact, lots of triangles, over 200,000 triangles. And the resolution goes from about 5 kilometers at the boundary here, down to between 100 and 500 meters at the coast, depending on where it is. And the reason these are so difficult to see is because these are the higher resolution elements. So I'm just going to show. So for example, this plot is zoomed in of this area, and you can see that the size of these triangles, so the resolution gets finer around the coastline and through, for example, channels around southern Espiritu Santo. So that's one of the really good advantages of these sorts of models, that we can get this resolution transition very easily, and so it much better captures processes that are happening in coastal and shallow regions. The other thing that's important about this model is that it has wave flow coupling. And so what that really means is that important processes are passed between the wave component and the hydrodynamic component of the model at set intervals. And in our case, it's every few minutes. And this can be really important because there are nonlinear interactions of ocean waves and currents, and they're important for lots of nearshore applications. And waves can have a strong contribution to water levels and coastal processes such as storm surge and extreme water levels. And including waves in the model can improve the elevation and storm surge simulations. And that's shown just as an illustration. This is for not for Vanuatu, but for somewhere else. But it just shows as an illustration the impact of including waves in a model. So in these two plots, the circles are the observed storm surge. It's a storm surge event when you had elevated water levels here. So the circles are the observations. The red line is the model simulation, which when the model included waves, and the blue dashed line is when it didn't include waves. And you can see by including the waves, you get a much better simulation from the model. So as we said, this is going to be used to produce early outputs of water levels in our 40-year hindcast and to simulate extreme event scenarios. And so this is, going to be a very good resource, but it's to be able to get a model of this scale and at the resolution that we have got it at, it's highly dependent on three main things, which is reliable bathymetry at the appropriate high resolution, appropriate forcing data, and then observational data against which to calibrate and verify the model. So I was just going to flip through some of these. So as you know, EMAP was contracted and provided the satellite-derived bathymetry. which is at very high resolution for shallow water regions at 10-meter resolution. And they've also provided a multi-source bathymetry data set, which includes the satellite-derived bathymetry and also chart data at 4 spatial resolutions. And the multi-source bathymetry is shown here on the plot on the right. And you can see the actual, sort of the resolution of that bathymetry data. And we wouldn't have been able to have done this numerical modeling without this data set, without this high resolution bathymetry. But it's not only important for the model, it's also a highly valuable resource for Vanuatu, for other sectors and other applications. Okay, why don't you want to move? Sorry, my screen's just frozen again. Okay, here we go. Sorry, there's a bit of a lag for some reason. The other thing it's really dependent on is good forcing data. And so one of the forcing data sets we're using, forcing for waves, and we are using that Corker hindcast that Ron mentioned, because that's available at the required timescale. It's over that 40 years, and it's available at hourly timescales to input to the model. So we've done some verification just in terms of making sure that this is suitable for our application. And so the plots on the left here just show wave propagation of waves during Cyclone Harold through the domain. And this was just checking that wave heights along the model boundary were appropriate. The other thing it needs is good forcing data for winds and mean sea level pressure. And that's also coming from the hindcast. And this just shows the track of Harold through Vanuatu. These middle panels is just verifying that the sort of picking up the tropical cyclone in terms of the appropriate wind speeds and getting the wind directions correct. So these panels, each one is an hourly time step. It starts here and goes across the page like this, and it's just showing that the winds during the cyclone, and this is just a zoomed in. So we did some verification just to check that these winds are going to be appropriate for the model, and that's fine. And we've also done this for TC-PAM and TC-IB. So the other thing that's really important to be able to have this national scale model at such high resolution requires considerable calibration and validation, but it's got a lot of process to take into account and to get right. So the calibration involves sensitivity tests using trying different parameters for hydrodynamics and waves, as well as getting appropriate seabed friction values, which are known as bottom roughness. So different seabed types have different friction coefficients, and we've utilized that high resolution bathymetry from EOMAP. Plus we've also done some, so in certain key areas, we've also used the Allen's Coral Atlas habitat mapping. So you see these are the plots in the middle here are showing the different habitat types from this Allen's data set. And then that corresponds to different seabed friction values that we're using within our model. And that's currently being sort of fine-tuned in our calibration steps. And so initial validation, this is showing water levels for Port Vila at the tide gauge during April 2020, when Cyclone Harold came through. The black line is the observations, so the observations from the tide gauge, and the red is our model simulations. And the top panel is the total water level. The middle is the water level that's is the tidal component of that total water level. And then the bottom panel is the basically what's left over, those non-tidal elements that's contributing to those water levels. And so we're doing these sorts of validation also at Luganville and for the other cyclones as well. And this is part of our fine-tuning step, and you can see it's doing a pretty good job, but we're doing sort of further fine-tuning. In terms of validation for waves, we really do need good wave data to validate our modelled wave outputs. And I think Ron's going to talk a little bit about that in the next talk as well. And just in terms of next steps, so we've done much of the hard but really essential groundwork, and we're just going to finish fine-tuning the model. We'll then do the 40-year hindcast, which is very easy to say, but it's certainly not trivial, to run one model month. So for example, to run April 2020, takes 1.5 hours on the Australia's national computing infrastructure high performance supercomputer. So it's quite intensive, as you can imagine, with all those triangles. Then we'll analyze the outputs, also not trivial, produces a lot of data. And as I've said before, use that to refine the total water level, extreme value analysis, etc. And then we'll explore the simulations of synthetic tropical cyclones, which I think Ron's going to talk about next. Okay, thanks. I will stop sharing there. Sorry about the problems with the presentation. And Ron, I think that's over to you for the next one.
Yep, thanks very much, Vanessa. Let me just see if I can find what I'm supposed to be sharing now. There we go. Can everybody see the agenda?
Yes.
Yep.
All right, great. Yep, so thanks very much, Vanessa. That was a great background into the national scale dynamic model that we've been building as part of this project. What I wanted to talk about in this next short talk is really two things. One that Vanessa alluded to before, and that's using the national dynamical model to explore sort of in a stochastic fashion. I'll explain more about that in a moment. The synthetic tropical cyclone populations that are coming out of activity 1.2.3. And also, as Vanessa promised, to talk a little bit more about the ocean instrumentation that is also part of this project, and the dynamical model calibration and verification. So to get back into the synthetic cyclones and the stochastic processes that I was mentioning, this statement at the top of this slide was on my last caveats slide of my last presentation in this workshop. And that is, again, despite the fact that Vanuatu as a country experiences tropical cyclones quite often, sometimes several times a year, any particular location within Vanuatu will only see severe impacts from a tropical cyclone typically every few, maybe 10 years. What that means is that calculating exactly what the 1 in 50 year or 1 in 100 year storm tide or storm surge or average recurrence interval, ARI, is a bit tricky, and there's a lot of uncertainty around that. That's of course making the assumption that you're doing this off of historical observations or off of a single scenario dynamic simulation, such as the 40-year hindcast that Vanessa discussed performing in her talk. And just to sort of demonstrate what I'm talking about, on the bottom panel here is a time series of wave heights for a location offshore from Port Vila. And what we can see here is that, you know, there's our 10-year ARI, but actually only one storm has really crossed that. That was Tropical Cyclone Pam. Tropical Cyclone Pam had very unusually high wave heights because of its track and its slow forward speed as it approached Vanuatu. And so you can see that on our return interval, our ARA plot here on the top. You know, TC Pam really, in terms of wave height, it's not talking about wind speed or storm surge, but just in terms of storm waves, Tropical Cyclone Pam was much higher than these other storms. It was a bit of what statisticians might call a gray swan event. And so that the heavy black line in that top plot then is a fitted extreme value curve. And the dotted lines are the 95% confidence intervals. And so really what that means is if you calculate the 50-year storm wave height from this location, it's 9.1 meters. But the uncertainty bounds are between 4 and 14 meters. So if you're considering port operations or coastal defenses, it's a bit less than optimal to have to design for some range between 4 and 14 meters, for instance. And so basically what this is telling us is that that 40 years of deterministic data is actually not very good for estimating these design storm heights, if you like, these ARIs, without very high uncertainty. And this is a problem everywhere in the world where there's tropical cyclones, but particularly in the Southern Pacific and Indian Oceans, where thankfully tropical cyclones don't happen as often as they do in the northern Western Pacific and in the Caribbean and Gulf of Mexico. So recognizing this issue, in earlier studies for the PACSAT program, we addressed this by looking at these synthetic tropical cyclones in Fiji and Samoa. And so those are just some studies that we performed in that. However, the KIRAP activity 1.2.3 that Dewi gave the workshop on 2 months ago, I think you recall that Hamish Ramsey provided an overview of some of the synthetic tropical cyclone populations that they are generating for Vanuatu as part of this project. Those are actually much more scientifically advanced, much more cutting edge than the synthetic cyclone populations that we developed for those earlier studies in Fiji and Samoa. So if we combine those synthetic tropical cyclones, or that stochastic or probabilistic approach to cyclones, with the dynamical national coastal hazard model that Vanessa just presented, we've really got an opportunity here to reduce the uncertainties associated with these tropical cyclone coastal hazards, and also to perhaps get a better handle on how the tropical cyclone hazards might change in the future, rather than just assuming sea level rise and maybe some assumptions about slow changes in tropical cyclone intensity and frequency. So this is the two figures on the bottom here are just an example of some preliminary work we've also done in Queensland, which the left panel just shows all of the tropical cyclone tracks in the historical tropical cyclone tracks in the ID tracks database. I can't remember off the top of my head, but I think it's something like 40 or 50. And then the right panel shows a similar synthetic tropical cyclone population, just one of several tropical cyclone populations, but that particular population has over 4,000 tracks in it. So that just gives us a lot more data to analyze and therefore to reduce our uncertainty in any given location's tropical cyclone associated coastal hazard impacts. Of course, we can't dynamically model all 4,000 cyclones in every single tropical cyclone population. That would blow up Australia's supercomputer that Vanessa was talking about. So we need to do some statistical tricks here. And this is one we're investigating, which is to do a cluster analysis of all of the characteristics of the tropical cyclone population. And that's so the cluster, the subset defined by the clusters are the blue dots you can see in the plots on the right here. Whereas all 4,000 cyclones are the gray dots. And what you can see is the blue dots effectively cover the probability space of the tropical cyclones. In other words, this reduced set of 300 tracks statistically represents all 4,000 tracks. So instead of dynamically modeling 4,000 tropical cyclones per synthetic tropical cyclone population, we can model 300, which is more computationally trackable. Once we have these downscaled synthetic cyclones, we can then reconstruct that into locally relevant coastal hazard information with reduced uncertainty compared to just the historical or single scenario dynamical simulations. It's this stochastic versus deterministic approach. However, there is a big caveat here, for this to work and for it to effectively reduce our uncertainty, we really need to be able to trust the skill of our dynamic model, that is our national schism model that Vanessa presented. And at the present moment, we really don't have enough observations to, as Vanessa said, calibrate and validate or verify that our numerical coastal hazard model. So right now, as you've seen, we're relying pretty much only on the tide gauges at Port Vila and at Luganville. And these initial comparisons are pretty good. Like, for instance, on the left here, that's actually, that comparison is between the total water level calculated not even with the downscaling model, but with the national data from the regional climate information that I presented in my first talk. You can see that looks actually a very good statistical comparison with the tide gauge. And then the other figure there on the right is the one that Vanessa showed, comparing the dynamical downscaling model with the Port Vila tide gauge information. But again, tide gauges are in deep water harbors. I would expect these comparisons would not be as good if we looked around the corner at a more ocean exposed location. But we really need some observations there so that we can better understand how well our dynamical model works before we cut it loose on some synthetic tropical cyclones and use it as a tool to reduce our uncertainty. And in particular, as again, I'm repeating what Vanessa said here, in particular, it's a lack of wave observations to calibrate the model is what's needed. So obviously I'm very excited that Van KIRAP project has bought 6 wave buoys and a number of pressure and temperature sensors that we can use once they're deployed to verify and calibrate our dynamical models. What I'm presenting here, this figure on the right, is from a study that was actually done in the Marshall Islands, which created some very good inundation models for the airport that you can see on the right there. And that's just an example of some deployment configurations for the SOFAR wave buoys and the RBR sensors, which actually we discussed yesterday. Some of us discussed yesterday. You know, in a transect across the reef from deep water up across where the waves break and towards the shoreline. And so again, I don't think we need quite that density of observations, but this is just an example of a sort of a recommended configuration that if we were able to deploy this sort of configuration would really help us to verify and calibrate that national dynamical schism model that Vanessa presented, and thus reduce our uncertainty in coastal hazard information that we can provide to Vanuatu through Van KIRAP. So in summary, we still plan to deliver all of this information. Tentatively, that's our plan, to deliver all of this information in the same way as I presented on my last slide or at the end of my last talk, which is average recurrence intervals or the storm tide levels tied to different climate scenarios and also including current climate. And so I'd just like to return to those earlier questions of discussion. For discussion, I think our discussion period will follow this talk immediately in the agenda. So again, I would really like to ask everyone on the line to consider, you know, if this is the most useful way to deliver the information to the project, and if so, what storm tide levels are already being used, if they are in Vanuatu. You know, how should this information, could this information be delivered through the portal or otherwise? Is there interest in related climatology products on waves and tides? And if so, what would that look like? And of course, any other questions or comments on what Vanessa and I presented so far today. And I think that's it for the presentation parts of 1.2.4.
Great. So are we happy to just get into some questions from Vanessa?
Yep, that would be great.
So maybe if there's not anything immediately, maybe I'll just ask Sunny for some comments on the presentations.
Thank you. Thanks, Rebecca, and thanks, Ron. Our team in the BMGD conference room here have been listening, and I'll probably open up the floor for any comments from BMGD, as well as the sector representatives in the House.
This is Ron. I'm happy to go back on any of the slides, and I'm assuming, Vanessa, you wouldn't mind either going back to any of your slides if anyone would like to return to any of the slides for questions or comments.
Yeah, no problem at all. I guess one of the things, was there any comment around the periods of the design? We were talking about the 1 in 10 year, 1 in 50 year. That's probably quite an important thing for us to understand, isn't it, Ron, in terms of priority of kind of what's important?
Yes, I agree,
Sector
Vanessa.
scale, yeah.
And just also any thoughts on, you know, and this actually could be from Stafford or Nathan, any thoughts about how this might be delivered in the portal, although we have some time for that later in the workshop as well. But yes, I agree, that's quite an important thing to think about, Vanessa. And look, it could be that some of the sector leads need to consider this talk a bit more, and so happy to take things later, but if there's any questions or comments now, happy for those too.
Sunny, I think. Ron, thank you very much for the presentation. There was in one of your slides you showed analysis or the readings you're getting from the two type cages, one from Port Vila and the other one from Glenville. Are you also assessing the two type cages, you know, the data from the two other type cages belonging to the Chika project, one from Lenakel, Tana, and the other one from Leeds install Leeds Wharf on Malekula?
I think the short answer is no. Maybe Vanessa, do you know? I feel like I've heard of this data, but we haven't been able to get it yet. It would be very valuable if we could get it. Do you know more, Vanessa?
No, I mean, we don't have that data yet, but yes, please.
Yes, if there's any way we could source that data, I mean, we're data hungry, observations hungry here.
That would be very useful for us if we could share data so you run those studies. So the analysis that will help us here, especially for the producing marine forecast products that will help our communities here, especially around the southern part of the Vanuatu, the Tafea, and also at the Malam province. And even as you can see there, there's nothing there in the top province.
Mm-hmm. Yep. Yes, if you could, so are those tide gauges in Tana and Maukula? Does BMGD have that data then, or I guess where can we get it?
Yes, I think we have it here, but we'll get, maybe we will talk to the management if possible. We can share the data to those analysis.
Great.
Yeah, that'd be great.
So Ron, Sunny here. I think some quick reactions to the presentations. I think my own personal take, and then BMGD and the food sector coordinators will also share their thoughts on the presentations and the different types of ARIs that you mentioned. We appreciate the 10-year ARI and the 50-year, but we haven't looked at other similar work in other countries where 100-year ARI are also provided, which is probably the extreme in terms of the types of extreme sea levels that one side or one particular country can experience. So I think for the purposes of planning and looking at certain applications of those sort of extreme levels of events, like similar to the one like you've shown about the tropical cyclone Pam in 2005, I think those are very useful, future insights into the sort of inundation that the extreme sea level can provide to a certain place. And I think the usage of smaller circles and triangles as a point really also links really well to any on-site or site-specific activity that a sector is working on. So I think rather than doing a large box, I think having those points like in circles or triangles really help for sectoral application of that information, because some of the work that the infrastructure are looking to do using the climate change projections, if we're looking at road infrastructure or bridges along those coastal areas, and they will be looking at the nearest circle or the nearest triangle and extract the best information on how they improve the designs and look at potential relocation or adaptation options for those particular locations. So I think in terms of ARI, I think adding the 20-year and the 100-year will be very useful. That's my own personal take. BMGD and the sectors will also voice their feelings and their advice on the issue. But I think the way that the information has been presented using those the way that you've done it has been very useful, and I think it will be easier for us to use relevant points to a certain activity around the vicinity of a location. Especially now for tourism as well, we're looking at a certain place around the Champagne Beach, Lonham Beach. So we'll be looking at those circle points, extreme sea levels around that area, because it's perhaps the most useful information that we can extract from the projections to really inform and advise the type of intervention that we can do on the ground, whether it's soft solution revegetation or perhaps looking at hard solutions like putting in coastal protection mechanism or something similar. So those are just preliminary responses, but thank you very much.
Ron, there's also another question in the chat if you wanted to answer that one, which says, are we also considering terrestrial waters climate projections?
So I guess to answer that question about the terrestrial waters, in this activity, no. Activity 1.2.3 is providing some information in terms of rainfall, and I think perhaps if Dewi is online, she can speak to that, because I'm not quite sure where 1.2.3 was going with. I know they're doing extreme rainfall, but not sure about stream flow and things like that. So, I think that's like sort of compound event flooding, where we're trying to think about like the combination of storm surge and say, river flooding. That's perhaps a little bit beyond the scope of this. We could consider to at least think of looking at it at a case study location. There was some discussion of that in Luganville and the Sakata River. But again, I think we need to think about that a little bit. And I'd like to have a discussion with Dewi and some other folks in activity 1.2.3, because again, that's a joint probability problem, right? We need to think about how to hook those up there. That's a whole nother statistical analysis, I guess, for the joint flooding. And again, I don't know. I think I saw Dewi online. I don't know. She has more comments.
Yeah. Hi, everyone. It's Debbie here. So in response to Ron's comment and to the people who asked the question, for the stream flow analysis, especially flood, it will be beyond the scope of the project. So that is number one. Number two, we already trying to look at the stream flow data in Santo, for example, that Jonas have given us, in an effort to explore whether we can develop hydrological model for that catchment. But the data availability doesn't allow us to do that modeling yet. So the short answer is we will not be able to produce the stream flow projection for this project because it is beyond the scope of the project. Also because the lack of data for the hydrological observation. So I hope that answers the question.
There's nothing else in the chat. I mean, if no one else has a question now, we could take a break earlier and then people can have a chance to think about some more questions through the break. And then we can just check again quickly after the break, if we'd like.
One more question from this end, please, Rebecca.
Of course.
In this particular slide that we're seeing right now, slide number 23, there is dotted points that are in colored different colors. There's red points and there's yellowish blue points.
Oops, sorry. Oh, sorry. There we go.
Is our interpretation of the red points, are those hotspot sea levels, extreme sea level points? Can you clarify, please?
Okay, sure. So this is just some preliminary example data of that. The national scale information derived from the regional modeling products. That does not include the wave run up and wave setup calculation. So this is the 1 in 10 year, I think, height, considering tides, sea level variability, and inverse barometer So, I mean, look, I forget exactly, apologies, I didn't put the color scale here. But it's not an enormous variation. It's like a difference of 10 or 20 centimeters, I think, across from the blue to the reds. So I guess I'm pained to say that this is preliminary data. It doesn't consider all the variables. So, and it's not a huge range because again, it's really the wave exposure that will probably make the biggest difference here. And we're still refining the wave run-up and wave setup algorithm. And of course, we want to improve all of this information with the dynamical downscaling model also. So I guess what I'm saying is, yes, it does indicate that there is higher water levels on the eastern sides of the islands towards the south, but that it's preliminary data. So please let us come over it and do some quality control here, and don't take too many, don't try and take too many insights at this time, please.
Thank you, Ron. Yes, we note really well the explanation, but yeah, but what we want to comment on or provide feedback on is that this is the sort of a presentation of the results that will make it really easy for the non-technical people to really understand which are some of the areas that there's a little bit heightened risk in terms of extreme sea level. So I think after having all the hard work and the verification done, I think this sort of presentation at the end of the variability of the risk in different areas will definitely be really helpful. And we also need to communicate the confidence and the different levels so that when people use the information, they know the uncertainty, they know the risk, and apply that information appropriately so that it's making an impact in the planning and the execution of the different climate change interventions. I hope I'm making sense, but I think we will work to communicate the data using the different codes and explain it to the users at the end, especially the sector users and policy people.
No, thanks very much, Sunny. That's great. It's good to know that we're on mostly the right track. And so my main takeaways so far, before we go on our break then, is that we need to add the 1 in 100 year ARI to our analysis. And we need to see if we can chase after that tide gauge data from Tana and Mount Tula.